Okay, I have found the button. I am assuming that this is working, because it's on. We'll just have to try and see, and then if there's no sound, I'll have to try it again. Okay, so I'm going to do a video on weak dispersion forces. And so firstly, where are we going to see weak dispersion forces? And this is going to be between the structural portions of molecules. So remember, with the structural part of the molecule, that is where we have carbons and hydrogens. And so, because we've got carbons and hydrogens in our structural part of our molecule, and these are the only kinds of bonds we have present in our hydrocarbons, then weak dispersion forces are the only kinds of attractions between hydrocarbons. Okay, so how do they occur, or what are they? They are temporary dipoles. And so we know that a dipole happens when we've got a small amount of charge present. So for example, with our carbonyl group, we know that the oxygen is more electronegative than the carbon, and so it ends up with a greater share of the electrons from the bond than the carbon does. So this is a permanent dipole, because that uneven sharing of the electrons happens all the time. A temporary dipole occurs when we've got uneven sharing of electrons that happens momentarily. And how that will look is if, just say for example, this hydrogen ends up moved out a little bit further from the carbon than its regular bond length, if you like. And so because it's further away, it's going to be slightly positive, and the carbon then will be slightly negative. And so this then becomes a temporary dipole. And if we've got an adjacent molecule, then just say same thing's happening where this one is stretched and that's slightly positive, and my carbon there on that second molecule is slightly negatively charged. I'm going to have an attraction occurring here between the slightly positively charged carbon and the slightly negatively charged carbon, and the slightly positively charged hydrogen on adjacent molecules. And then what happens is that a moment later, next time we look, that hydrogen's gone back into its regular bond length, and maybe another hydrogen has moved away. So what we've got is this dynamic movement of the atoms involved in the molecules. They're not fixed. When we make our models using the molecules, it seems like they don't move, but they can and they do move. And so why do you think a bond might stretch? What would we need for it to stretch? Energy. Okay, so I add a little bit of energy into this, then particles move. The more energy there is, that we're going to have more movement. And so just so happens at this moment when we had a look, this was the one that was moved away most from the chain, and so slight positive, slight negative, and then this is going to happen on adjacent molecules. So that is what they are, is a temporary dipole, and it's on the structural portion of molecules that have functional groups, or it's just on our hydrocarbons, because that's all they have is carbons and hydrogens. Now, one of the other questions that someone had asked about was ranking boiling points, and so if we look at that example of what's happening with the temporary dipoles with our hydrocarbons, if I have ethane, it's a very small molecule, isn't it? And so there aren't many opportunities for it to interact with an adjacent molecule. So if I have another molecule of ethane here, the chances of this aligning so that maybe this hydrogen is stretched and this hydrogen is stretched so that we can have an attraction there is pretty small. There aren't that many places where these adjacent molecules can interact with each other. Therefore, okay, so these are interactions between temporary dipoles. Unlikely. Low boiling point. Okay, we've got minimal attractions between the molecules. But if I come along then and I have something like octane, don't line them up. Now we've got many more possible locations for these interactions to occur. Okay, so we could have a stretch here, and that's slightly positive and slightly negative. Now remember, this is just temporary. And then maybe that happens over here as well. So these are going to be attracted through there, and yep, we could have it happen here as well. So hopefully you're getting the picture that if we have a longer chain, and our example was hexane, there are more opportunities for temporary dipoles to interact with adjacent molecules. And that's going to increase the boiling point. Increased. Compared to our short chain. But remember that these weak dispersion forces, because they are only temporary dipoles, are then the weakest of those intermolecular forces. And so even though I've said that my hexane here has an increased boiling point, if I had a functional group on here, then that would change that. So for example, if I add a halogen or something onto here, then with that halogen added on, I now have a permanent dipole present on the molecule, and these would have a higher boiling point than the parent alkane. Does that make sense? So I'll do a little bit more about ranking the boiling points with functional groups, but this is just to say that if we've only got our carbons and hydrogens, then we only have weak dispersion forces, which means that we have temporary dipoles that have these momentary attractions between molecules, and they're going to have the lowest boiling points of all when we compare them to a molecule that has the same structure, but has, if they have functional groups that have a permanent dipole or hydrogen bonding, then their boiling points will be higher.